thank you for everyone who's here and come to listen, and thank you to my hosts. So my name's Nathan Gambling. I'm probably better known for hosting the podcast Beta Talk, which is found on all sort of places you find podcasts. And I started that up about 5 years ago to disseminate and amplify the voice of really good heating engineers, because I realised it was a voice that possibly wasn't involved as much as it should be in the discourses around decarbonising heat. So the agenda today is I'm going to be talking about the challenges of engaging with tenants. And to do that, I'm going to help you all understand heat, not heating. Whenever I talk about heat and heating, I use a historical context. I never like to be described as a great heating engineer. There's plenty of women and men out there that are fantastic heating engineers. I suppose my advantage was my grandfather was one of Europe's leading combustion engineers and R&D engineers when domestic central heating first started to become popular. So we're going to also at the end talk about some practical ways to engage with tenants and outline the importance of data collection. So engagement is challenging. Heating is complex, and if I'm honest, the knowledge around it is very poor. And it's not any. If you're involved with social housing or local authorities, it's definitely not your fault, because knowledge around heat and heating is poor across the heating industry, all the way up to the manufacturers. One of the things I like to always sort of talk about is that there are different types of engineers. So let's use my dad as an example. Bless him, he retired during COVID. He probably wouldn't have retired, but he retired during COVID at 74. He had customers old enough to be his parents. He covered 176 rural villages, and all he did was repair oil boilers. So if you go without heat and you're elderly, you possibly die. So he was very, very good at getting boilers working again. Now, that's very different to engineers that are great at designing heating systems and putting systems in that are very efficient. My dad wouldn't have a clue how to do that, but he could get your heating going if it was an oil boiler. It helped his father-in-law helped invent some of this stuff, but he was very good at that. So there are different types of engineers. So the types of engineer that are engaging with occupants of homes is quite important. Do they understand how this stuff works, or are they just good at repairing it? One of the challenges in the UK is we're a very crowded market. We've probably got the most crowded market in the world. And since domestic heat, central heating, we've always been able to heat homes, individual rooms, whether it was a paraffin heater, a log burner, or your electric bar fire. But when central heating became popular, it was very notable that the UK, everyone that's involved in heating entered into the UK market, and they're all trying to sell us stuff, basically. And arguably, a lot of the knowledge has attenuated over time, and we have lost a lot of common engineering, common sense. When you engage, obviously, we live in a wonderful, diverse society. So the homeowners, they're a diverse cohort. Us engineers are extreme heterogeneous bunch. So that's a very big challenge when you're trying to explain complex things to tenants. Heating systems are complex. Now, one of the things that does help engagement is if the person doing the explaining has some very good knowledge. And this is where it's all falling down. There is, unfortunately, poor knowledge around heat and how heating systems work. It probably sounds quite strange for me to say that, but that is the truth. Today, I'm going to help you understand heat, not heating, so that we can help disseminate this good knowledge that we all kind of, if you're going to be engaging with tenants, we kind of need to know. So there's me measuring my cup of coffee. So temperature and heat are different things. They've obviously got a relationship, but they are different things. No one has to know the laws of thermodynamics, but if you want to, the zeroth law is all to do with temperature. First law is all to do with energy, and the second law is all to do with entropy, if you're interested. So temperature and heat obviously have a relationship, but they are different things. Lots of people are talking about low temperature at the moment, and it's causing confusion. And one of the ways I help people understand this is a 1960s home could be heated with low temperatures. That sort of probably confuses a lot of people. You didn't need to be insulated. So all these old leaky homes we talk about could be heated with low temperatures. They always have been. And we're going to sort of discuss that as we progress through the presentation. So this is really, really important for people to understand. So we get heat and light from the sun. We all know that light has a constant speed, the speed of light. I can never remember what it is, but we all know that light has a constant speed. It's very important to realise heat does not have a constant speed. Its speed constantly changes. And this is so important to remember. So when I talk about heat, I get people to just, if you ever hear the word heat, just flash these images up into your brain to realise heat is always moving at different speeds, because it's very important. What makes heat move at different speeds? Well, it's all to do with the difference between 2 points. We've got heat moving outside of a home, and we've also got heat moving into the home. The difference between the temperature inside your home, which is usually going to be around 21, if it's colder outside, heat will move quicker out of the home. And the same with radiators. You can push heat into a home quicker if the radiators contain higher temperature water, because the difference is greater. Now, I'm very aware that I'm probably confusing people already. So what I do is I use this analogy, a seesaw. So I've got 2 seesaws here, and I've put a ball at the top of the seesaw. Now, instinctively, we know that that ball will roll to the low point. So gravity dictates that the ball will roll from a high point to a low point. And that's exactly what heat does. Heat will move from a high temperature to a low temperature. Now, if we look at the second seesaw, we can see that there's a greater difference between the high and the low points, and we therefore know that that ball would roll quicker. It's exactly the same with heat. Heat will move quicker if there's a greater temperature difference. And if you look at the table on the left, I've got some red numbers. So if it's -3 outside, there's a greater difference between outside temp and indoor temp. So the heat is going to move through your home quicker. But it's really important to understand that the heat moving through your home is constantly changing. It all depends on what that temperature is outside. So on the right is something called a Mears calculator. That's my old Mears calculator. So people were doing heat loss calculations on homes many, many moons ago. And heat loss from an uninsulated 1960s home at design outside temperature. What is DOT? What is design outside temperature? So we've all heard of people doing heat loss calculations, whether it's the surveyor or whether it's an engineer. So what we're doing when we design a heating system, we want our heating system to be able to push heat into the home quick enough to match the speed of heat leaving the home. So we have to pick a speed. What we do is we pick the average coldest temperature of the UK. Now, the average day in winter is going to be around 7 degrees, but the average coldest day is going to be around -3. Now, obviously up north, it's around about -5. In London, it's -1.8. But across the UK, the average coldest temperature is -3. So what we're going to do is design a heat system to be able to push heat into the home quick enough to match the speed of heat leaving the home when it's -3. Now, what that means is at different outside temperatures, the speed of heat leaving the home changes. And if we look at this slide, look at the bottom row, which I've put in red, we can see that if it's 10 degrees outside, which is quite cold, you know, people are going to put their hats on and their coats on still, the speed of heat leaving the home is halved. And this is in an uninsulated home. So it doesn't matter whether the home's insulated or uninsulated, heat is still going to move. It will always move if there's a temperature difference. Insulation just slows things down. But if it's 10 degrees outside, we've now halved the speed of heat leaving that home from when it was our design outside temperature, which is -3. So we now know that heat moves at different speeds. It moves at different speeds out of the home. What it should be doing is moving into the home at different speeds via the radiators and the underfloor heating. Virtually all social housing, virtually all private housing is moving heat into the home, though, at a fixed speed, and generally far too quickly. We've fixed that speed as if it was -3. So we're pushing heat into the home always far too quickly. And this is why TRVs were introduced into domestic central heating and why wall thermostats were introduced, because we were moving heat into the home too quickly. We needed things to turn it off. Now, we've got these things called smart stats. They look lovely, but they also are just turning things on and off. Now, there are some smart stats that can control the speed of heat, but they've got to be wired up to the boiler properly, and generally they're not. Now, there was an excuse for moving heat into a home too quickly back in the day before the condensing boiler, but there isn't any excuse now. So here I've just got a table. This is the heat loss from a home, and what I've done with the red writing is just you want to put heat into the home and match that speed. Okay, so just highlighting that you push heat into, you're supposed to push heat into the home at the same speed as it's leaving the home. That's where we get our efficiencies. But what are we doing? This is what we did in a 1960s home. We didn't push heat into the home at the same speed it was leaving the home. We constantly pushed it in at top speed at 10 kilowatts, which is the same as saying 10,000 joules per second. We were constantly pushing heat into that home at a very, very, very quick speed. So I've done a little funny here, if you just have a little look at that. So you're sitting at home, it's -3 outside, you're comfortable because your radiators are pushing heat into the home at the right speed. But you get above zero, what's happening? It's starting to get a bit hot in your room. So what do? You think, well, it's getting too hot. You can either get up and open windows, or better still, you turn the boiler off. Now, once you turn the boiler off, you've got no heat pushing into your home, but heat is still leaving your home. And then what happens is, well, you start to feel a bit chilly. So out your chair you go and turn that boiler back on again. And you're going in and out of your chair all day long, turning the boiler on and turning the boiler off. Now, of course, that's a bit impractical. So what did we do? We had these things that did it for us. These things turn the heating off, and then they turn it back on again, then they turn it off, and then they turn it back on again. And the reason they do that is because we're pushing in heat into our homes too quickly. Now, lots of people will think these were introduced into the heating sector back in the day as energy saving devices. They were not. They were introduced into the industry because we had to push heat into our homes far too quickly. So if you want to have a little look about what the flow temperatures we actually needed in the 1960s home, remember this is an uninsulated home, these are the actual flow temps we actually needed. If it's 10 degrees outside, we only needed flow to the rads at 50 degrees because you're changing the speed. You don't need to keep pushing the heat in at the same speed. But what did we actually do? We always had flow temps of around 80. We always had a return temp of around 70. So we're always pushing heat into the home far too quickly. So this table is just to illustrate that we could have low flow temperatures way, way back. Obviously, as you're aware, there's a lot of scared or people, there's this fear about you can't use heat pumps because they're low temperature systems. All heating should be variable temp. You shouldn't have it fixed at high and you shouldn't have it fixed at low. It should be variable and change the temperature depending on how much speed you need to go into the home. Also worth remembering, this all happened with single panel radiators. There were no K3s back in this day. And the single panel radiators, don't get me wrong, became corroded very quickly because one of the problems with high temperature heating is it exasperates corrosion. The process of corrosion speeds up when we use really, really hot temperatures. So let's explain why we overheat homes and why we're still overheating homes by pushing heat into the home far too quickly. So when you burn coal, wood, oil, or hydrocarbon, we know that CO2 is produced. That's why we're all here today. But inside that flame is also water vapor. You cannot see it. Now, a flame is very, very hot. It's over 1,000 degrees C. 54 degrees C is actually quite hot to us. It's going to be quite scalding to skin. But to 1,000 degree plus flame, it's piddly. And what happens is that water vapor in the flame, when it hits a metal surface, will condense back into a liquid. Not a very nice liquid either, quite an acidic liquid, quite a corrosive liquid. And what that would do is, if you've got your flame inside your boiler and it's hitting that metal box that contains the water, that water's going all around your rad system. If that water is lower than 54, the water vapor in the flame condenses back and it spot corrodes the water jacket, the heat exchanger. And that's expensive because boilers back in the day were expensive. 1963, you could buy an oil boiler for the same price as a brand new mini car. So there was a problem. The engineers that were involved in this central heating industry back in the day realised after the 73 fuel crisis that it would probably be better if they could invent boilers that could deal with this condensate problem. And my granddad was one of them, and he was half Dutch. And in 1981, the first condensing boilers came to the market. And that meant now we didn't have to have fixed flow temperatures. We could change the flow temperature with compensation controls. So a compensation control looks at the weather temperature and it then talks to the boiler. It says, hey, it's -3 outside. We need high flow temps. Hey, it's 10 degrees outside. Our flow temps to the radiators do not have to be so high. So it's communicating with the boiler, telling the boiler to change the temperature that goes to the radiators. And you can do that quite easily. It just turns the flame down. Just like on your stove, gas stove, you turn the flame down to simmer instead of boil. So you're telling the flame to sort of calm down a bit because we don't need high flow temps. Compensation controls have been around a long time. These are some from the 1980s. But what are we doing? We still put heating systems in today with on-off control. And some of our thermostats look wonderful. They look lovely. You've got flashing lights. You can connect to them with your phones. They've got geofencing on them, but they are still controlling boilers with a fixed flow temperature, which means we're always pushing heat into the home far too quickly. Therefore, we've got to keep turning it off, then on again, off, then on again. Not a great way to heat your home. Why are we doing this? Well, that's the $6 million question. One of the reasons is I think that lots of people don't understand the building regulations. Even people that are in working groups helping write the guidance for the building regulations arguably don't understand. If you read the approved document, and obviously approved document part L is what we're mainly concerned with here, every approved document tells you that most of the words are guidance. It's only the text that's written inside a green box that's the requirement. And if we look at the requirement in part L, 3 words: have effective control. Thermostatic room controls, that 520 you see at the top, that's just in guidance. That's a clause from guidance. And if you read the manual to the building regulations, it will state you do not have to follow the guidance in the approved documents to meet the requirement. The requirement is have effective controls. Now, the control industry is extremely powerful, has been extremely powerful for a long, long time, quite a few decades. And I think they quite like the idea that we're going to have thermostats in all different rooms and TRVs here, there and everything, rather than just one thing, a compensation control telling the boiler what to do. So we've lost a lot of knowledge around why thermostats were introduced into the industry. Even the manufacturers have forgotten why their product was introduced into the heating industry. It was introduced to turn things off because we overheated homes. And that's just at the beginning. It just shows you at the beginning of every approved document, it tells you that it's only the text in a green box that this actual requirement. English law isn't silly. It's not going to tell you you must use a TRV because someone might invent something tomorrow that does the job better than a TRV, and you've now put into law that you must use something. So the regulations aren't prescriptive. And I think lots of people think the guidance are the actual regulations. The guidance is just there to help you meet the requirement, but it doesn't mean you have to use it. And arguably, I would argue that an on-off control strategy is not effective controls. Remember, the requirement is to use effective control. I'd argue that using on-off strategy is not effective, and so would a lot of other people argue that as well. Engaging tenants. So we need good knowledge. If we're going to start talking to tenants and trying to explain heating systems to them, the people explaining do have to have a real good awareness of heat and how we heat homes, how we should heat homes. It's going to be hard, let's not make too many bones about it. Engaging people is hard when it comes to heat systems. They don't particularly want to know about the heat systems, they just want to be warm. Historically, you'll find most plumbers and heating engineers, when they go into people's homes, there's confusion around what is the actual boiler. So people look in their cylinder airing cupboards and they will look at the cylinder and point to the cylinder and call that a boiler. But one thing people do seem to understand about their heat system is what a radiator is. So we can use that. We can get people we can engage people with the radiators. Now, ironically, as important as radiators are, they are very misunderstood. Lots of confusion around radiators. Even with, once again, radiator manufacturers, I go and speak to a lot of radiator manufacturers at the trade shows. None of them really know kind of how heat is moving into the home from them. And if people that are engaging with occupants are confused, then occupants are going to be confused. So I'm going to quickly show you a little bit about radiators. Remember, this is recorded, so you can come back to it and use it as a resource, because I'm very aware that this might sort of seem quite complex at the beginning for people, but please use this as a resource and come back and watch it as many times as you need to. So if you go and buy a radiator like this, 600 by 600, that means it's 600 high by 600 wide. It's a type 2.1. It's got 1 convector, 2 panels. That will say it's an 807 watt radiator in the catalogue. But if you have a flow going to 60 and a return of 50, it's now 482 watts. If you had a flow at 60 and a return at 40, it's now 389. Interestingly, the power increases if we have a flow of 55 and a return of 50, because we've got a wider delta T now between the average temperature in that radiator and the room temperature. Remember, it's the difference between them two that drives the speed of heat going into the room. So what a radiator can do is always changing. Remember, we shouldn't have fixed flow temperatures going to radiators. They should always be changing. Just to confuse people even more, if we drop the room temperature, that radiator becomes even more powerful because the temperature difference is now greater. Remember the slide, or the seesaw, sorry, the greater the difference, the ball will roll quicker. We've now got a greater difference between the room temperature and the temperature inside the radiator. So the heat will move in quicker. So radiators are very, very important in all heating systems, but obviously very important in heat pump systems. And when people are trying to describe heat pump systems to occupants, I've noticed that a lot of engineers and anyone doing the liaison is struggling to understand. They talk about oversized rads and undersizing, but they don't really understand what a radiator is doing. One of the things I think we can engage occupants with is their radiators. Most people aren't going to understand all that stuff about watts and joules per second, and why would they need to? But I do think we need to engage people somehow with their heat system, get them talking about it so that we can then sort of explain some other concepts to them. So we're all very used to our mobile phones now and taking pictures. So I developed an app where you could take a picture of your radiator and it would tell you what your radiator can do at all these different temperatures. And again, the occupant might not understand that, but the person, you can either get them to take the picture, or the person doing the surveying can go, hey, would you like to use the iPad and take a picture of your rads? And we're going to learn all about how much heat is being pushed into your home. So you start to engage people. And obviously this technology can be white labeled for whoever wants to use it. And of course, when you're collecting all this data as a social housing provider or a local authority, you want to be able to actually do something quite useful with it. And that's where one of the companies I'm with is we can do digital twin simulations. We can use artificial intelligence to work out, what homes have what radiators, what can be heat pump ready overnight. And that then helps informs decisions, and also with local area energy plans, it can help us really sort of start to plan this stuff well. So the moral of this is, if we're going to engage with people, we've got to have people doing that engagement have some real good understanding of heating systems. And I really want to stress, definitely no one's fault, especially in the social housing sector or local authority sector, that there's this poor knowledge, because the poor knowledge exists in my community of engineers, and it's perhaps not their fault either, because basically they've been marketed to just to sell stuff. So they get trained to safely install stuff. They don't get trained around sites of heat, really. They're getting trained to install stuff safely. And then it's just a massive marketing bonanza. Everyone wants to sell them stuff. So unfortunately, a lot of knowledge has been attenuated that we started out with when we first started to put domestic central heatings into the UK. So you can always listen to me on my podcast. I waffle on probably even more than what I've done today. My podcast is called Beta Talk, and then you can contact me at learn at Beta Teach. I help people understand heat. So obviously I do a bit of consultancy work. I consult for people like Nesta and various other people. And you can find me at Nathan at Jawn. And that's a new company I started up with a friend of mine who comes from the oil and gas background, where he pioneered the sort of the digital twin architecture for gas exploration. And for obvious reasons, he wants to come across, and he's come across into this sector to help with this sector now. So thank you very much for listening to me. Thank you very much.